an old lab. Uh, it's gone through a few iterations. It used to be in the regular. You can see that, right? Electromagnetic
Yeah.
induction. You can see that on the screen.
Yes, I can see it.
Okay, yeah. It's a pretty poor copy, but it'll work for what we need to do. I did not last Friday, but the Friday before. I went into the lab and actually performed this experiment, and I did it in a few parts. So I'm going to post the videos just like I do the lectures for online. Um, but the idea is that whenever you have uh, coil of wire, uh, when well, let me stop the share so I can demonstrate. Um, how do you? Oh, there it is. Okay. Can you go ahead and mute your mic? Because I think that'll allow me to, or I don't know, maybe. Do you see my full image? Because I'm seeing a big image that says Tomas Alvarado.
Yeah, I have the camera off. I can turn the camera back on if you want.
No, that's not necessary. Uh, I'm gonna
Yeah, I
have to
can see the full
find
image.
that. I'm sorry, what?
I can see the full image.
Okay, if you can see the full image, we're gonna have to do a lot of pretend here. If we just imagine this to be a coil of wire, when you put a magnet through the coil of wire, it induces a current. And that's what we're going to be studying. We're going to be studying the currents in a coil of wire. Uh, so we're going to be passing a magnet through, uh, and we're going to be um, pulling the same magnet out. Now there's uh, for the most part, the magnet is going through with the north first, let's say, and I just put it in, and then I withdraw it with with the uh, I just withdraw it from the coil, and I've got a galvanometer that you'll see the current on the galvanometer. Now I used a small magnet, uh, and so as I put it into the coil, and it's actually a long coil. Maybe I should, yeah, it's more. This isn't a coil. This is just a little syringe, but we'll imagine it having a coil of wire. You'll see it when I post the videos. It's a small magnet, and so as I put it through the coil, the north goes in first, but it's so small that as it exits, it's a growing north field, but then it's a collapsing south field. So you'll see the meter do one of these. Ordinarily, when I'm using just a large magnet, it increases and then it decreases as I pull it out. Well, with the smaller magnet, it's an increasing north, and as I go beyond the coil, it's a decreasing south. And so as I pull it out, it's an increasing south and a decreasing north. So you'll see this double kick action on the galvanometer. And then there's parts of it where uh, I have one coil, and then I have another coil, and I'm inserting it. Again, these are not coils. It's just I didn't bring them home, so I have to just use something to imagine. If you put energy uh, onto the uh, primary, it generates a magnetic field, and that changing magnetic field as it grows will induce a current onto the secondary, and you'll see that it's a very slight increase in current. But once I put an iron core to increase the permeability, the current gets much greater. Um, so that's what we're going to be doing. Let's go through the lab. Let's see. I lost. Where is? Oh, here it is. Okay. So uh, this equation, this 39.3, this is you induce a current when you have a changing magnetic flux. Well, phi, the d phi dt, the phi part of it, if you look here at 39.1, the magnetic flux phi is the magnetic field times the area. It's a dot product, B dot A, so it ends up B A cosine theta. So if you need this changing magnetic field, d phi over dt, that's equal to the minus the this expanded version of it. You can probably use your calculus and come up with this derivative, and you'll see that there's three parts here. You can have dB over dt, that's a changing magnetic field over time, or you can have this dA over dt, which means you have the changing area over time, or you have this d cosine theta over dt, which is what? That would be a changing angle. So if you have this, if you have this coil, let me stop the share to get the image up. If you have a coil of wire, this is just a little elastic band. If you have this coil of wire, you'll get a current if you change the magnetic field, putting a magnet inside and out, and that's how a lot of generators work. Hydroelectric power, you're turning a magnet. You're either turning a magnet inside large coils of wire, or you're turning the coils of wire inside a steady magnet. Or you can change the area. You can change the area. That's a little difficult to do, but there's part of the experiment that you can see how the area is changing. Or you change the cosine theta. You rotate this in a magnetic field. That's how motors work. So that's the key. This 39.3 is the key. A changing magnetic field, the changing of the area or changing of the angle. And so we go through the procedure. The first thing I recorded on this experiment is establishing the positive and the negative on the galvanometer. Once we do that, then we put a magnet through the coil, and when we see the deflection in the coil, we'll know which is positive and which is negative. And you can see that inserting the magnet will give you one deflection, and then withdrawing the magnet, you get the other deflection in the opposite direction. So I'll do that part of it. Then I do a induced magnetic field, and that's where we have it's just the primary, which is the smaller coil, and all I do is take a little magnet and move the magnet around, and you can see that the magnet indeed is pulled by the coil. And then I don't know that I did the Lenz's law. I think there's enough there that in the other experiments that I do, that you can see the result of Lenz's law. And if you remember Lenz's law, the current will be induced from, like, if you have a growing magnetic field, it's going to induce a current such that it opposes the growing magnetic field. I discussed this in the last set of lectures that I produced. If you have a collapsing magnetic field, it's going to induce a current such that it wants to reinforce the collapsing magnetic field. And that's Lenz's law. And then we do the permeability experiment, where we have two devices. A primary coil and a secondary coil, and we just look at the effects when we have we just really have two cores. One is an air core, and one is a iron core. I didn't have any other steel or copper or anything like that. They would have been reduced, but it's enough to just do the air core and the iron core. And you see that the iron core produces a much stronger result. And then let's see that later, we're going to do the length of the coil, and showing this because what we're going to do is we're going to put the primary inside the secondary with the iron core, and we're going to move it by 1 centimeter and measure the fall off of the current, and we'll do that, and I'll provide all the data. I won't do the experiment for you, but I'll provide you with enough data that you can perform all the equations, all the necessary calculations that are needed. And so, do you still see me up in the corner of the screen?
Yeah, yeah, you're coming out perfect.
Okay, all right. So in that first part, I'll do it slowly, and you get a small deflection. And if I do it fast, you'll see that you get a larger deflection. It's very specific. It's not specific. They just say V. You do it at 1 motion, V1, and V2 is a greater motion, a faster motion. So that's part of the experiment. And then I think we do the permeability, switch open, switch close. There's only air core and iron core. This one that has a blank core, you can forget that. And then we have the data table where we have the length of the primary. I think it was like 10.5 centimeters or something like that. I recorded the data. Well, as a matter of fact, I should. Well, I won't take the time to look at it now, but I took the data, and I even used my slow-mo camera on my phone to record the exact. I think when I'm talking on the video, you can't really see it, but I repeated the experiment off camera with my cell phone, and I took down the data. So I'll have that data on the deflections, and then you just fill out the average. And then there's a question, and you can see this question here. This first one, this is a changing area. Remember I said you can change the magnetic field, or you can change the area, or you can change the angle. Well, here's one where you're changing the area. You can see that this small rectangle is a smaller area than this larger rectangle, and so it's changing. So that's there's a question that involves a changing magnetic field. I mean, I'm sorry, a changing area. The magnetic field is constant, uniform B field, but the area is changing, and that's pretty much it. So I'm going to be producing videos tonight, or I have the videos. I just have to assemble them and make pages for it on Canvas. And
we're gonna have the air core, and then you're gonna say switches closed, switches open on your video, right?
Yes.
Yeah, and then we'll put the results down, plus or then the secondary will be the same way. Okay.
Yes, and I'll provide you the data. I'm not expecting you to try to read it off the computer screen.
Okay.
Okay.
And then our V1 and the V greater than V1 will be the data that we get. Okay.
Yeah, that's just the velocity. Once I do it like real fast, and then I do it again slowly, and that's a very relative term. How fast you push it in, and how slowly you push it in. All of that is relative. So that's kind of an intro to the
experiment lab.